3.5 is division of whole numbers. We're going to pick up where we left off last time. We're about to take a look at whole number properties, just like we had looked at whole number properties with our three of our four other operations. So this section is going to feel like subtraction. We're trying to see which of these properties will hold by verifying if we can make them not hold. And in subtraction, we saw none of them held because we always found a way that we could make it not work. So the first one is talking about closure. So closure happens when we take a closed set, or take a set, like whole numbers, and that's what we're working with here. And we operate with the given operation, we're working with division, to see if we get another whole number. Now sometimes we do, right? 4 divided by 2. It's 2. That would actually be in our set. But can you give me an example of one that doesn't work? We're looking for 2 whole numbers that when I divide it, I don't get a whole number.
3.
Okay, Kaylee, let's go.
3 divided by 5.
3 divided by 5. This is not a whole number. What was your example, Mackenzie?
2 divided by 4.
2 divided by 4. Just flip my fraction that I gave an example of upside down. Yep. And we could go on like that all day, right? Yeah. In particular, anytime the numerator is smaller than the denominator, it's not going to work. And sometimes when the numerator is bigger, it's still not going to work. So yeah, this is not going to be a property. The closure property is not a property of division. Commutative property means that the order of the division needs to not matter. So in particular, if I did something like, so this is an example, 6 divided by 3, or 3 divided by 6, do I get the same answer? No, I don't. In fact, one of them is a whole number, the first one, right? But 3 divided by 6 is actually 1/2. Not only is it not a whole number, but it does not equal 2. So commutative doesn't work. The order of division matters. Order of multiplication doesn't. Order of division does. Associative. Yeah, this is going to fail too. So I'll give you an example of one that fails. We'll do 12 divided by 4 divided by 3. 2. Sorry, that's what I have here. 2. And then the question is, does it equal? Not it does. The question is 12 divided by 4 divided by 2. So on the left-hand side, we do the 12 divided by 4 first, and we get 3 divided by 2. What's 3 divided by 2? It's not a whole number, right? It's actually the number 1.5. It's 1.5. But it's not a whole number, you're right. I'm actually going to leave that off for the moment. On the other one here, what is 4 divided by 2? 2. And 12 divided by 2 is 6. Whoops, a little too low. 6. And once again, it doesn't equal the 1.5. So there's no commutativity and there's no associativity. Both of those fail, as well as closure. Identity. Is there an identity element? The answer is no. It almost looks like there is. Right? Let's say we took the number 1, because it's the likely candidate. 5 divided by 1 is 5, and it works halfway. But the properties have to work in either order. So the identity property is only true if I can flip the order and it also works. And what happens when I try and flip my order? It does not work. It does not equal the same value 5 that I began with. Division by 0 property. Well, division by 0 property would have to say that if you did 0 divided by 2, you got 0, and it does. That's good, it checks out. But what happens when you have 2 divided by 0? Is it? Okay, let's actually talk about why this works, because it's really important and it's often a place of confusion. 2 divided by 0 has to, or in our minds should, maybe will, equal something. Let's just call it A. Okay? Well, by definition, from division, last time, the very first slide we did back at the beginning, this has to be able to be taken, this 0, over to the other side with multiplication. And it would have to be the case that the 0 that I just moved times the A is equal to 2. What's 0 times A? 0. And 0 times anything will always be 0. I can never get back to the 2, right? There's no way to get back to the 2. I can't divide by 0 and get back to 2. So from the very definition of division, this is not defined, does not exist, is not defined. You can use any of those words if you'd like, but at the very least right now, they're not the same. Okay, does that make sense? From a concrete example, if you're trying to explain it to a child and you're like, they're not going to understand this whole definition thing, you can also talk about it the way we talked about it from a picture standpoint. You're like, okay, well, I have 2 objects and I want them to put them into groups of size 0. How many groups of size 0 do I have? Well, it doesn't make sense, right? Or you can say, I want to put 0 of them in a group. How many groups do I have? Right? Like you can use that kind of language and it just won't work. Because we can't make groups of size 0 and actually get anybody into a group. Okay? All right, last one is the distributive property. The distributive property, kind of like the identity property, almost works. Or you can say it works in one direction. The 0 property actually worked in one direction as well. So if we have something like 20 plus 10, and we have it divided by 5, then what it would have to be true for the distributive property work is that this is equal to 20, actually let me write it that way, 20 divided by 5 plus 10 divided by 5. And this actually works. What's 20 plus 10? 30. And what's 30 divided by 5? 6. On the other side, 20 divided by 5 is 4, and 10 divided by 5 is 2, right? So on the left we have 6, on the right I have 4 plus 2. That worked, didn't it? So the distributive property, if I do it in this order, seems to work. But it has to work in either order. So let me show you where it fails. It's when we flip things, right? So let's do it as 20 at the beginning. And we're going to divide by 10 plus 5. And the question is, does it equal 20 divided by 10 plus 20 divided by 5? All right, so what's 10 plus 5? Because that's the parenthesis part on the left. 15. The left-hand side says 20 divided by 15. On the right-hand side, what's 20 divided by 10? 2. And what's 20 divided by 5? 4. So on the right-hand side, I get the same 6 that I had a moment ago. Is the left-hand side equal to 6? No. 20 divided by 15 is a little bit more than 1, and it's not a whole number either. So this piece is not equal, which means that it fails here. So once again, the answer is no. It's just like subtraction. Everything fails. Okay, all of our properties fail to hold. Yep. It is. Did I write something wrong? I did. Sorry. 0 divided by 2 is 0. Typos on the screen. So sorry. I was so excited to get on to the next one. I was just moving too quickly. Thank you for fixing that for me. Oh yeah, 0 divided by 2. And we can actually make sense of that in groups too. I didn't mention that, but while it doesn't make sense to divide something into a group of size 0, you can take 0 objects and divide them evenly. It sort of sounds funny to do so, but if there are 0 cookies in my house, then every child gets the exact same number. It's easy, right? It doesn't matter how many kids I have. So yeah, you can divide by 2, the 0 divided by 2, but we can't do the other one. Thanks for fixing my error. Okay, there are actually only 2 division algorithms, okay? The standard algorithm, which you know, and then there's one called repeated addition, which will look like something we introduced last time. Okay, so let's do the standard algorithm first. We have 623, and we're going to divide by 5. What the standard algorithm does is it relies on the fact that you know your multiplication tables. So, some of you have expressed the lack of remembering your multiplication tables, and you might actually find it difficult, depending on what we're dividing by, to make this work. The other thing that causes problems with the standard algorithm is if you're trying to do division by something that's not in a multiplication table. So if you're good with your multiplication tables, dividing by 5 may not be a big deal, but dividing by 22 might. Right? I don't know my multiplication tables of 22s. So sometimes the standard algorithm, while we could do it, is not something that's quite as straightforward as if it's smaller numbers because we've memorized. So the standard algorithm works something like this. We take the number 5 and we ask how many times does it go into, and we'll start with the first number, 6. So how many times does 5 go into 6? 1 time. So we write the 1 on top of the 6. Then we multiply 1 times 5 is 5, and we subtract. So 6 minus 5 is 1. Now 5 won't go into 1, so we bring our next digit, the 2, down. How many times does 5 go into 12? 2. So we write the 2 above the 2. We multiply 2 times 5 to get 10, and we subtract to get 2. We bring the next value down, it's a 3. How many times will 5 go into 23? 4. 4 times 5 is 20. And for the purposes of this course, we're thinking, right, lower level grades, we're doing remainders. Right? When you work into elementary, when you move from elementary into middle school, you use things with decimals and fractions and stuff like that. That's not what we're doing right now. This 3 at the end is our remainder. You usually call it an R value, right? The end. And so your answer from up here is 124, remainder 3. Now, sometimes you don't have a remainder, and that's fine, but sometimes you will. But all of that really, really hinged on you knowing something about the multiplication tables of 5s, right? It does. And not only do we not always know the multiplication tables of a value I'm dividing by, like I gave an example of 22, there are some children with learning disabilities who don't have the ability to memorize in the same way that you and I might. Like there's really a mental block that doesn't make that work. And unless they have access to a multiplication table, they're at a disadvantage for something like this. You tracking with me on that? Okay. So I'm going to show you another algorithm. There's more steps involved, but it doesn't rely at all upon your ability to multiply. Okay? So, yeah, well, you're clapping now. We'll see what you think in a minute. All right, 623. What we're going to do is we're going to do repeated subtraction. Now, do you remember when we talked about this on Monday, where we kept subtracting 6 rocks and 6 rocks and 6 rocks a bunch of times until there was 0? Mm-hmm. Yeah. Well, we don't want to subtract 5 from this, hundreds of times. Like, that's not a cool idea, right? We don't want to do that. So here's what we do. We look at the first digit that the 5 will go that is smaller than. So that's actually our number 6. So we put a 5 underneath this, and we put the numbers zeros next to them. What we're actually doing is we're multiplying 5 times 100. We're doing a 5 with 2 zeros on. There's 5 hundreds. All right, so 5 times 100. And so we subtract this. So 623 minus 500 is what? 123. Can I subtract 500 again? No. So I go down one place value. So instead of subtracting 500, now I will subtract 50. I can still do that. 123 is big enough. 50 is 5 times 10. That's what 50 is. So when we subtract 123 minus 50, You can do regrouping and so forth, whatever it is you prefer to do for subtraction on that. What is 123 minus 50? 73. Can I, oops, I don't know why I have a negative there in front. Can I subtract 50 again? Yeah. So we will do it again. So this is another 5 times 10. All right, so what is 73 minus 50? 23. Can I subtract another 50 again? No. Okay, so obviously the more times that I have to subtract 50, the more annoying this process would become, correct? Just like when I did the 6 and the 6 and the 6 and the 6, it becomes more tedious the more times I actually have to subtract something. Okay, so I've done the 500, and I couldn't continue. I did the 50, now I can't continue, so what will I subtract next? 5. So what is 20? Oh, 5 is actually just 5 times 1. What is 23 minus 5?
18.
Okay. Can I subtract a 5 again? Mm-hmm. That's another 5 times 1 over here. What's 18 minus 5?
15.
Can I subtract a 5 again? Actually, let me move it over here. I've got more space. A little bit. 5 again gives me 8. It's another 5 times 1. Can I subtract 5 again? Promise we're almost over. 5 times 8 minus 5 is 3. And that last one was a 5 times 1. Can I subtract 5 again? No. So my answer is actually over here. You might be saying, where, Dr. Hands? Well, there's a 100. There's 10, 20. And then I've got 1, 2, 3, 4. There is 124. And my remainder at the bottom was 3. So you're counting up the multiples of 10 that you have on the right-hand side.
But technically, they still have to know their multiples of 5.
Nope, they have to know multiples of 10. And all multiples of 10 are 10 times 5 is 50. 10 times, or 100 times 5 is 500. It's just the number with zeros tacked on. Anytime I multiply by 10, I just put a 0 on the end.
So,
I'm not sure that's a big ask, Kaylee, because we're just putting zeros on something. That's not really multiplication. Do you see what I'm saying? So if I wanted to multiply, for example, times 10,000, no matter what number you give me to start with, all I have to do is write that number down again and write that many zeros, 1, 2, 3, 4 zeros. And I'm done. So that's the only sort of quasi-multiplication that's going on, and it's just tacking on zeros. Okay, the rest of what we're going to look at, I think all 3 of them that are left, or the next 2 rather anyway, the next 2, are application problems with with the different operations that we've done, not just multiplication or division, but with all the processes that we've done. So we have Juan. Juan saved $5,340 in 3 years. If he saved $95 per month in the first year and a fixed amount per month during the last 2 years, how much did he save per month during the last 2 years? Okay, so this is a multi-step problem. There's multiple things going on. It's the individual steps that will require either multiplication, division, addition, or subtraction. And then we can use any of the standard algorithms that we know, or we can use any of the alternative algorithms that we've learned. Okay, so taking a look at this problem, what might be your first step to do?
figuring out how much you saved in the first year.
Okay, figuring out how much he saved in the first year. And what did it say about that, Kinsey?
You said 95 per month.
95 per month. And how many months are there?
12.
There are 12 months. So we might do 95 times 12, right? You can do that lots of ways. What you might do is you might do breaking up and bridging. That's the one I see right now. I like that 12 is 10 times 2. So I could do 95 times 10. And I could do 95 times 2. And I could add them. So this 95 times 10, Kaylee, is another example of multiplication with a multiple of 10. So if I have 95 times 10, it's 95, and then I tack on a 0. What's 95 times 2? Well, if you weren't sure, you could add it together, right? 95 plus 95. That would be a reasonable thing you could do. You can use a standard algorithm since I've kind of got it set up that way. That's what I'm going to do. So 5 times 2 is 10. I'll regroup my 1. 2 times 9 is, plus 1 is 19. And then if I add these together, 950 plus 140, you end up with 1140. So this is $1,140 the first year. Now that's not the answer to my question, but it is a step along the way. What would I do then with that number 1140?
Subtract it from 5340.
Okay, so 5340 minus 1140 is actually a very nice subtraction problem because it doesn't really involve any regrouping, so there's no need to do anything to shift things around. What is 5340 minus 1140? 4,200. What would I do with the 4,200 then?
Divide it by 24.
You can divide it by 24, and we could do that. There's nothing wrong with that. There is an easier way to do it, though. Did anybody think of another option? Okay, so Kinsey, tell me, why do you want to divide it by 24?
Because there's 2 more years and we need to figure out how much you save per month, so that would give us the answer.
Yes. So we could definitely divide by 24, and there's nothing wrong with that. I don't want you to hear me say that that's a wrong answer. But we also could divide by 2, which you can probably see real easily what this would be divided by 2. And then we could divide by 12, which is smaller. And so it's a little bit preferable. So definitely not the only option, but if I were to take 4,200 and I were to divide it by 2, what would I get? 2,100. And then I would divide the 2,100 by 12. Now, I'm going to do it with repeated subtraction because I want you to see another repeated subtraction, okay? So this is 12, and then it's 100. So I did 12 times 100 here. And I subtract, and when I subtract, I get 900. I don't have this one written down, so make sure I'm watching to make sure I'm not making a mistake, okay? I think we're at 900. Can I subtract 1,200 again? No. So what would I subtract next?
12 times 10.
12 times 10, which is 120. And we're going to have to do that one quite a few times. So this one would be 0, 8, 70, 780. And I'll do a 120 again, which would be 660. And again, should be 540. And again, which will be 420. How do you like this process, Kaylee? Change your mind?
Yes.
Okay, so it definitely has disadvantages if it goes in enough times, right? It does. This would be 300. We are nearing the end, though. 12 times 10. At least the end of the 120s. 120 again gives me 180. I have 180 at the top, so I'm going to start back with 180. 180 times, minus 120 is 60. So that's the point when I can't divide or subtract the 120s anymore, but now I subtract
Just the 12.
12s, and I do them one at a time. So this would be 8, so I've got 48. This would be 36. 24. And then I have 12, and lo and behold, eventually I end up at 0. Ugh. I agree with you. Ugh. We gotta count them all up though. Okay, so there's 100. So 100. How many tens?
7.
yeah, I think there's 7. Did you count too many in there, Mackenzie?
Yeah.
Okay. 7. How many ones did we use?
5.
There are 5, I believe. Make sure on mine. 1, 2, 3, 4, 5. So it's 175. And the units are dollars, so we want to make sure we write down the dollars on it. Okay. One more word problem. Dan has a lot of pennies. He's apparently been collecting for quite some time. 4,520 pennies in 3 boxes. He says there are 3 times as many pennies in the first box as the third, and there are twice as many in the second box as the first. How much money does he have in each box? And I read this and I almost feel like it should go back in chapter 1. The penny question. I think we even had something a little bit similar to this in that section because it's a good problem-solving question. Huh?
It was like this exact same thing, but with dimes.
Yeah, did we have one with dimes? So I know we had one similar with coins back there. Okay, so we've got 3 boxes. I think at least it would help me to see some boxes written out so that we can actually talk about which box is what. So we have 3 boxes. And there's a total of 4,520 pennies. He says there are 3 times as many pennies in the first box as the third. Well, I don't know what's in the third, but we're just going to call it, well, we'll call it P for pennies. P for pennies. It says there are 3 times as many in box 1. How would I label box 1 then?
There's 3 times as many in box 1.
Mm-hmm.
P times 3.
P times 3 or 3P, either way. And then it says there are twice as many in the second box as the first. Not 2P, that would be twice as many in the second box as the third. Yeah, 2 times 3P. Twice as many in the first box as in the second box as the first. So we could put that, or we could actually write 6P if we'd like at that point. All these pennies, if you dump them all together, add up to 4,520. So 3P plus 6P plus 1P or P is equal to 4,520 pennies. Okay, so what is 3P plus 10P, 3P plus 6P plus P?
I'm so confused why we put the 3P there
Where?
in the middle box.
Because it says there are there are twice as many in the second box as the first. The first box had 3P in it.
Oh, I thought that was the first box. Okay.
Yeah, I just did them from left to right in order. Okay, how many P's do I have?
3.
Nope.
A lot. 6.
How many?
Yeah.
10. How'd you get 10, Mackenzie?
I had 3, 6, and 1.
Yeah, we add the coefficients together. 3 and 6 and 1 would be 10P. Equals 4,520. Okay, what would we do to find P then?
Divide by 10.
Divide by 10. And dividing by 10 is lovely because dividing by 10 makes zeros go away on the end if they're like that, or it makes decimal points move if we're working with that. So my 4,520 becomes 452. Now, we solved the problem. We didn't answer the question. The question says, how much money does he have in each box? So you can answer one of 2 ways. This 452 is the number of pennies in which box? The third. So box 3, you could actually say has 452 pennies. That's okay. Or you could even say 452 cents. So 452 cents. Or you could say how many dollars? $4.52. Okay, those are all equal ways of writing it. Some more natural than others, but they're all correct. How can we figure out what's going on in box 2? Or box 1, sorry.
3 times 452.
Yeah, 3 times the 452. And I'm going to default to doing the coins one. So I'm not going to show the processes out, but what is 3 times 452?
1,356.
So do you mean $13.56 if you do it in decimal form?
Yes.
Yeah, okay. And again, you can not do it that way if you wish. And then box 2, you can either double the 1356 or you can multiply the 452 by 6. 2712. Okay, we have 3 questions left, but they're very quick. And then we'll finish up. The group work becomes homework, along with the homework, which will be submitted on Monday. Okay, because we won't be in class on Friday.
Are these problems long? Because there's not that many.
I don't remember. That's not a question I remember the answer to. I'm sorry. There are fewer things going on in this section, though, admittedly, right? And we only have 2 processes to do and things like that. So I don't know that they necessarily are, but there could be multiple parts, as there sometimes are. Mental math. The first one is breaking up the dividend. So sometimes it's really nice. And again, these are always sometimes things about mental math, right? When we notice a nice pattern. Sometimes it's nice to be able to break up the dividend. This is the break that we want here. Because we might happen to notice that the number nicely divides if I break it into 2 pieces, right? 63 divides by 9, and so does 18. Now, it's not equally nice to break it here, right? Like, that's not helpful. So there is a break, singular break, that's a helpful break here. So if I think about it like this, so we can write it as 63, and I can break it apart as 100 and 18, divide by 9. 6,300. How many times does 9 go into 63? It's 7. And so we have the 63 showing up here, right? That's zeroed out. So these 2 zeros come up. So this is 700. So 9 goes into 63 for 7 times. So 9 goes into 6,300, 700 times. How many times does 9 go into 18? 2. So this is 702. Definitely not going to work all the time, but when it works, it's really nice. Sometimes you can break up the dividend, but it's not as obvious, right? Like if I throw in here a bar right here, 25 looks really great, but 4 doesn't really. But 4 really means 400. You got it. So that's exactly what we want to recognize, is that sometimes there really is the ability to divide something once we put it into the place value that it's in. So how many times does 5 go into not 4, but 40? 8. And it's into 48 times, so it's into 480 times, because this 0 comes back up. And how many times does 5 go into 25? 5. So this makes 85. Okay, so again, will it work all the time? No, of course not. But there are places where it works and it's really nice. The last one is compatible numbers. Okay, so on this one, we could attempt to break things apart very concretely. This is not what this question is asking for. This is, notice the header at the top says computational estimation. Estimation means that we're getting an approximate answer. Pay attention to that description when you are trying to get an exact versus an approximate answer. What computational estimation does with compatible numbers here is it says, okay, I understand you've got 4,132, but what's a close number to that what will divide by 4 evenly and nicely and quickly and in your head? Yeah, 4,000, right? 4132 is not that far off from 4,000. So we do an approximation. We say this is approximately the same as 4,000 divided by 4. And what's 4,000 divided by 4? 1,000. Now, computational estimation may not be the exact answer, but if you were finding the exact answer and you knew that it should be about 1,000, it's a good check step to make sure that your answer makes sense, right? If you find this exact answer and somehow you find that it's 157, you should be alarmed and say, that doesn't make any sense. My answer should be about 1,000. Why am I getting 157, right? why am I off by a whole place value? Something went wrong, and I can go back and I can fix it. So even if it's not a problem requiring or asking for estimation, it's a good check step to see visually, does something I got make sense?